Hello and welcome back. In the last video, we looked at Layer 2 concepts. In this video, we are going to talk about IPv4 addresses. We'll take a look at the different classes of IP addresses, and we'll also talk about RFC 1918 addresses. We'll also practice decimal to binary conversion, which will help us to understand subnet mask in a much more easier manner. And then finally, we'll practice subnetting. Let's begin. IPv4 addresses. Now before we talk about IPv4, I want to take a moment and talk about the IP protocol itself. IP stands for Internet Protocol. It's the routing protocol of the Internet. IP is the protocol that routes your packets across all the routers in the world. There's another important thing that you need to remember, that things like guaranteed delivery of packets, and packet sizing. These kind of things are not taken care by IP. That's the function of TCP protocol that works over IP. Now let's talk about IPv4. When I heard about IPv4 for the first time, I was wondering what happened to versions 1, 2, and 3. Well, the answer is versions 1, 2, and 3 were not stable enough to be released. The first stable release of the IP protocol was IPv4, and that's why you don't have IP versions 1, 2, and 3, but only IPv4. Talking about IPv4 addresses, let's look at an example. So we have this example IP address 192.168.1.1. Every IPv4 address is a 32-bit address. If you ask how, every group that you see here is called as an octet. The reason they call it as an octet is because every group of numbers here can be represented in 8 binary bits. That's 1, 2, 3, 4, 5, 6, 7, 8. Every number here can be represented in 8 binary bits. That's why every number is actually called as an octet. You have a total of 4 octets. 8 bits per octet gives you a 32-bit binary value. The maximum possible value for any octet is 255. So the highest possible value for an IP address is 255.255.255.255. How do you get 255? When you put all ones in these binary bits, you will get the value 255. Each binary bit you see here represents a power of 2. It starts from 2 power 0 and goes all the way up to 2 power 7. When you add all these powers of 2, you get the value 255. We're going to discuss more about decimal to binary in the later topic. This is just for us to get started. The total number of IP addresses possible is 2 power 32. If you ask how, every binary bit here can either be a 0 or a 1. That's the only 2 values possible for every binary bit, which means there are 2 values, 0 and 1. There are 32 bits. 2 power 32 is the total number of possible IP addresses. However, not all of these IP addresses can be assigned to network devices. There are certain restrictions which we are going to talk as we move along in this video. Let's move to the next topic, which is classes of IP addresses. There are 5 different classes of IP addresses. The classes are Class A, Class B, Class C, Class D, and Class E. Class A starts from 0.0.0.0 to 127.255.255.255. Now this is a theoretical value. The reason I say this is because 0.0.0.0 cannot be assigned to any network device. That's why you say that it's a theoretical value. Class B starts from 128.0.0.0 all the way up to 191.255.255.255. Class C starts from 192.0.0.0 all the way up to 223.255.255.255. Class A, B, and C is what you use for assigning to network devices, to computers. Classes D and E are reserved. Class D starts from 224.0.0.0 to 239.255.255.255. Class D is reserved for multicast purposes. Class D is mainly used by routing protocols for sending routing updates. Class E, the last one, starts from 240.0.0.0 all the way up to the highest possible value, which is 255.255.255.255. Class E is reserved for experimental purposes. That's about the 5 different classes of IP addresses. It is always a good idea to remember the ranges of these classes of IP addresses, not just from an examination standpoint, but also because being a network engineer, it's really important that you know the basics like classes and RFC 1918 addresses. Let's dive into RFC 1918 addresses. RFC 1918 addresses. RFC 1918 talks about private IP addresses. Now, what do we mean by this term private IPs? Private IPs are those IP addresses which are free to use, which means you don't have to pay for or you don't have to register with your service provider to use these addresses. What's the benefit of using a private IP? Well, the number one benefit is that it is free and you don't have to register. That's number one. Number two, it helps to conserve the public IP address space. It helps to conserve public IPs. If you ask how, let's say you have a LAN that has 10 computers and each of these computers needs to have access to the internet. Now, if we did not have private IP addresses, we would have to assign public IP addresses to each of these computers to get on the internet. But now, since we have private IPs, we can assign a private IP to each of these computers and then we can map all these private IPs to one single public IP address and then we can go out to the internet. Isn't that really fantastic? So many computers having just one public IP address. Instead of having so many public IP addresses, we use just one public IP address. This mechanism is called as Network Address Translation, NAT. You don't need to worry about the specifics of NAT because we're going to discuss NAT in a future course, but the point I'm trying to convey is that private IPs help to conserve the public IP address space. Having said that, let's look at the ranges of private IPs. In each of the classes A, B, and C, we have a range of addresses that has been reserved for private IPs. The first one is 10.0.0.0/8, and the full range of this would be 10.0.0.0 all the way up to 10.255.255.255, and this belongs to class A. The second one is 172.16.0.0/12. So it starts from 172.16.0.0 all the way up to 172.31.255.255. And this is from class B. The third one is 192.168.0.0/16. The range would be 192.168.0.0 to 192.168.255.255. And this is from class C. It's a good idea to remember these ranges of addresses. Don't worry if you don't understand how these values translate to these ranges, because we are going to understand this in the next topic, which is subnetting and subnet mask. That's all about RFC 1918 addresses. Before we move into the next topic, I want to talk about another range of addresses that is reserved, and that's called as loopback addresses. Loopback addresses. The range of this address is 127.0.0.0/8, which means it starts from 127.0.0.1 all the way up to 127.255.255.255. This whole range of addresses is reserved for loopback communication. What do you mean by loopback communication? Communication to itself is called as loopback communication. A computer would use this IP address when it wants to communicate with itself. For example, one application on the computer is trying to talk to another application on the same computer. It would use the loopback address. We can even test this by going to command prompt. Go to command prompt and you can try to ping the address 127.0.0.1 and you are sure to get a reply because the computer is trying to ping itself. In fact, you can do the ping on any of the IP addresses in this entire range. The last address is the broadcast address. We can try the last usable address, which would be 127.255.255.254, and we get a reply. Right. So this whole range of addresses is reserved for loopback communication. Don't get confused. It does not belong to RFC 1918 addresses. That's all about RFC 1918 addresses and loopback addresses. Let's now dive into decimal to binary conversion. Decimal to binary conversion. There's a few different ways to convert decimal values to binary values. I'm going to show you the method that I use, and I personally find it to be very simple. So let's start. I hope you have a pen and a paper handy. If you do not have one, I strongly encourage you to get a pen and a paper so you and I can practice decimal to binary conversion. The first example is convert 16 to binary. To convert 16 to binary, we first write the number and then draw a couple of lines. The first line is vertical, the second line is horizontal. And then we start dividing the number by 2. How many times 2 is 16? 8 times 2 is 16, and the remainder is 0. Continue doing the same. How many times 2 is 8? 2 4s are 8, the remainder is 0. How many times 2 is 4? 2 2s are 4, with a remainder of 0. How many times 2 is 2? 2 1s are 2, remainder 0. Now don't stop here. We have to do this one more time. 2 zeros are 0 with a remainder of 1. You stop when you have a quotient of 0 and a remainder of 1. That's when you stop division. And then your answer will be in this direction. So the answer is 1 followed by 4 zeros. 0 0 0 0. That's 16 in binary. If we want to verify this, we can align the bits against the powers of 2. So let's align the bits 0 0 0 0 0 1, and then you add the powers of 2 corresponding to the ones. In this case, we only have 1 1, and the power of 2 corresponding to that is 16, and that's your answer. So we've converted 16 to binary, and we've verified that the answer is correct. Let's look at one more example. Convert 63 to binary. Start by writing the number and drawing a couple of lines, vertical and horizontal, and start dividing by 2. 2 31s are 62. The remainder is 1. 2 15s are 30. The remainder is 1. 2 7s are 14. Remainder is 1. 2 3s are 6. Remainder is 1. 2 1s are 2. And the remainder is 1. Don't stop yet. 2 zeros are 0. And the remainder is 1. When you have a quotient of 0 and a remainder of 1, that's when you stop. And you get the answer in the reverse direction. So that's 1 1 1 1 1 1. That's 63 in binary. Let's verify that quickly. Let's align these digits against the powers of 2. That's 1 1 1 1 1 1. And then you add the powers of 2 corresponding to the ones. So that would be 32 plus 16 plus 8 plus 4 plus 2 plus 1, which definitely is 63. Isn't that really simple and fun? Converting decimal to binary. I hope you enjoyed this. Now before we move to the next topic, which is Subnet Mask, I want you to practice a couple of more examples. The first one is try converting 34 into binary. The next one is 96. Finish practicing this and then we'll move on to the next topic, which is Subnet Mask. Subnet Mask. Every IP address can be divided into two parts. When we talk about any IP address, it contains two important pieces of information. Number one is the network address or the network portion, and number two is the host portion. Talking about this IP address 10.0.0.0/8, one part of the IP address is what we call as the network address or the network portion. The other part is the host address or the host portion. But how do we know which part of the IP address is the network address and which part is actually the host address? That's where Subnet Mask comes into picture. Subnet Mask is the 32-bit value that will help you to determine the network portion and the host portion in an IP address. Imagine this, you have your home address. Your home address has the street name along with the house number. In a similar fashion, every IP address has a network address which the router will use to forward the packet. The router forwards the packet to that network address, and then there's the host address portion which tells the router which host on that network does the packet belong to. So that's the role played by the subnet mask. Every IP address has to be accompanied with a subnet mask. Any IP address without a subnet mask, that is of no use, my friend. Remember this, it's a very important concept. Talking about the same IP address here again, let me put that again. 10.0.0.0/8. Now /8 is what is the subnet mask. The number 8 that you see here is the number of ones inside a subnet mask. Remember we said a subnet mask is a 32-bit number just like an IP address. Of the 32 bits, the first 8 bits are occupied by ones. The remaining 24 bits is the zeros. So if we were to write the subnet mask in binary format, this is how it would look. The first 8 bits are zeros. Are ones. And then you have 24 ones. And the last 2 octets, I'm just going to put them as zeros. Excuse me. So you can see the first 8 bits is what we call the /8. This is the binary representation of the subnet mask. If you were to convert this binary representation into a decimal representation, this would look like 255.0.0.0. If you ask how, you place these ones against the powers of 2. These are the first 8 powers of 2, starting from 2 power 0 to 2 power 7. Add the powers of 2 corresponding to the ones and you get the value of 255. That's how you get this value here, 255.0.0.0. So 10.0.0.0/8 is the same as writing it like this, is equal to 10.0.0.0.255.0.0.0. The ones in a subnet mask is what is called as the network portion. The zeros in a subnet mask is what is called as the host portion. So the ones will give you the network address, the zeros will give you the host address. Remember this, my friend. So in this example, 10.0.0.0/8, the first 8 bits represent the ones, which is the network address. The first 8 bits is the first octet. So your network address is this portion. And this portion is your host address. Another important thing to remember is, in a subnet mask, in a binary representation of a subnet mask, the ones and zeros will always be continuous. As you can see here, there's a continuous series of ones, and then you have a continuous series of zeros. That's how it will always be. There can never be a subnet mask like this. 10110. This can never happen. The ones have to be continuous followed by a continuous series of zeros. Apart from this, every class of IP address, class A, class B, and class C, has a default subnet mask. Let's take a look at it for a moment. Class A has a default subnet mask of /8, which means by default, a class A address has the first 8 bits reserved for network bits or the network address. Class B has a default subnet mask of /16. An example would be 172.16.0.0/16. If you were to convert this into decimal format, the subnet mask in decimal format would look like 255.255.0.0. Because the first 8 bits will give you this 255, the second 8 bits will give you this 255, and then 16 zeros will give you 2 octets of zeros. Class C IP addresses have a default subnet mask of /24, which means the first 24 bits are reserved for network addresses. An example of a Class C address would be 192.168.1.0/24. The decimal subnet mask for this would look like 255.255.255.0. Another important thing to remember is on any network, if you want to find the total number of host addresses possible, the formula for that would be 2 power h. 2 power h will give you the number of host addresses possible on any network. Let's take an example of a Class C network. 192.168.1.0/24. So the first 24 bits are reserved for networks, and the last 8 bits is what is for the host address. If you want to find out the total number of host addresses possible, that would be 2 power 8, which is 256. That's the total number of host addresses possible. But there's one more important thing to remember. The first address in a network is what is called as the network address. Network address, that's the first address. The last address of any network is the broadcast address. These two addresses cannot be assigned to any network device. The first address, network address, the last address, broadcast address. If we were to take the same example here, if we were to take this example, the first address would be 192.168.1.0. That's the network address. The last address would be 192.168.1.255. That's the broadcast address. So these two addresses cannot be assigned, hence the total number of usable host addresses would be 2 power h minus 2, which is 256 minus 2 will give you 254 usable host addresses. Remember, the total number of host addresses is 2 power h, but 2 addresses out of them cannot be used, so the total number of usable host addresses will be 2 power h minus 2. That's about subnet mask. Let's dive into subnetting. Subnetting. Before we start subnetting, or before we start practicing subnetting, I would encourage you to get a pen and a paper so you and I can do subnetting at the same time. It's going to be really exciting. It's going to be a lot of fun. We are going to practice a lot of examples. So go ahead, pause the video, get a pen and a paper, and we'll begin. Alright, I hope you're back with a pen and a paper. Let's now talk about subnetting. Let's talk for a moment and understand why we need subnetting. To understand the need for subnetting, let's talk about a Class A IP address, which is 10.0.0.0/8. Now let's just assume for a moment that this is a public IP address. I know you must be saying, hey, that's a private IP address. Yes, that's a private IP address, but just for the simplicity of this discussion, let's say 10.0.0.0/8 is a public IP address, and our organization has been given this public IP address. In the last topic, we learned that the total number of host addresses possible would be 2 power h. In this case, that would be 2 power 24, because out of the 32 bits, the first 8 bits are taken up for network, so the last 24 bits can be used for host addresses, which is 16.777.216. You remove the network address and the broadcast address, and you're still left with 16.777.214. Can you imagine that? So many host addresses on a single network. If you are a network administrator for such a large network, that would be a nightmare for you. So many host addresses to manage, so much of broadcast traffic, it's going to be unmanageable. That's reason number one. To make networks more manageable, we need to divide them into smaller networks. Let's look at another example. Let's say we have two routers. This is router 1 and this is router 2. And we have a point-to-point link between these two routers. We need to assign IP addresses to this point-to-point link, which is here and here. So we need 2 IP addresses for this point-to-point link. The class of IP addresses with the smallest number of host addresses is Class C because it has a /24 subnet mask. Let's assume we've been given a Class C IP address for this point-to-point link. The total number of host addresses or usable addresses would be 2 power 8 minus 2, which is 254 addresses. Can you imagine that? 254 addresses just for this single point-to-point link. We are going to use only 2 addresses, and 252 addresses are going to be wasted. That's reason number 2, to prevent the wastage of public IP addresses, or to efficiently utilize the public IP address space. Those are the 2 main reasons for us to get into subnetting. Let's look at an example. So let's say we have an organization that has been given a Class C IP address 192.168.1.0/24. That's the only network address that we have been given, and our organization has 5 departments. We have been told to put these departments on different networks, which means we need 5 different network addresses or 5 different networks for these departments. And we have only one address to play with, 192.168.1.0. So our task is to divide this address into 5 networks. Now, subnetting is a very, very simple topic, my friend. There's only 4 simple steps for subnetting. Let's look at them one by one. The first one says, convert your subnet mask into binary format. The subnet mask that we've been given is /24. Converting into binary format will make it look like this. That's the first octet. That's the second octet. That's the third octet. And that's the fourth octet. The first 24 bits have been taken up by network, so we wrote down 24 ones followed by 8 host bits or 8 zeros. Alright, so that's the first step. The second step says, determine the number of host bits to be borrowed. Now, why do we need to borrow host bits? We only have one network address, and we want to convert this one network address into 5 network addresses. Out of the 32 bits, the first 24 bits are already fixed. We can't touch them, so we only have these 8 bits to play with. So we need to borrow some host bits from here and convert them into network bits in order to get more networks. But how many bits do we borrow is the question, and that's where this formula is going to help us. 2 power x is greater than or equal to the required number of subnets. X is the value that we need to find out. In our case, 2 power x will be greater than or equal to the required number of subnets is 5. What is the value of x that will give you this answer? Let's say x is equal to 0. In that case, we are going to get a value of 2 power 0, which is 1. That's not what we want. X is equal to 1 will give you 2 power 1, which is 2. That is certainly not greater than or equal to 5. X is equal to 2 will give you a value of 4, which is again not greater than or equal to 5. X is equal to 3 will give you a value of 8, which is definitely greater than or equal to 5. So the value of x is 3, 2 power 3 is 8. So we need to borrow 3 bits from the existing host bits. So we have these 8 host bits here. We are going to borrow 3 bits out of them. So we are going to convert the subnet mask into something like this. You have the 8 bits, out of which 3 bits have been converted into host bits. Excuse me, the 3 bits have been converted into network bits by changing the zeros into ones. That's going to be your new subnet mask, my friend. Your /24 will now become /27. 24 plus 3 bits /27. That's your new subnet mask. The new subnet mask in decimal format will look like this. Let me just clear the board. Let's align the last octet against the powers of 2. We have 3 ones followed by 5 zeros. So we need to add the first 3 powers of 2, 128 plus 64 plus 32. That's going to give you 224. So your new subnet mask would be 192.168.1.0.255.255.255.224. That's your new subnet mask, or you can also write it as /27. You see how interesting this whole thing is? We completely changed the subnet mask to get more networks. Isn't that fantastic? Let's continue. We've not finished yet. The third step says determine the increment. Now what is the increment? Your first network address is 192.168.1.0. We need to find out the increment value which will be added to the original network address to give you more network addresses. I know that may not make too much of sense right now, but let's just complete step number 3 and it's going to be more clear for you. So let's focus on determining the increment. How do you find the increment? The increment value is the power of 2 corresponding to the least significant bit. Now what do you mean by least significant bit? It means the rightmost bit. So you need to find the power of 2 corresponding to the rightmost network bit. The rightmost network bit is this one. And the power of 2 corresponding to the rightmost network bit is 32. That is going to be your increment. So now we know the increment, which is 32. Now the final step is add the increment to get the new subnets. Let me completely clear the board now. We have the increment is equal to 32. We have the original network address 192.168.1.0. The last step says add the increment to get the new subnets. Now where are you going to add the increment? You need to add the increment in the octet from where you borrowed the bits. That is your 4th octet. You borrowed bits from the 4th octet, so you're going to add the increment in the 4th octet. Add 32 to this IP address, you get 192.168.1.32. That's your new network address. Continue doing that, you get 192.168.1.64. And then you get 192.168.1.96. And then you'll get 1.128. And then you'll get 1.160, 1.192. How many subnets is that? That's 1, 2, 3, 4, 5, 6, 7. You're going to get one more subnet because the total number of new subnets will always be equal to the power of 2. Here the power of 2 is 2 power 3 is equal to 8, which means you're going to get 8 total new subnets. This is 7. You're going to get one more. Add 32 to 192 and you will get 1.228 if I'm correct. Plus 32 for... Alright, that's 224. 224. So those are the new 8 subnets. The total number of new subnets will always be a power of 2. We got 8 subnets, which definitely covers 5 subnets. We only need 5 subnets, we only use 5 subnets, and we keep this for future purposes. That's all about subnetting, my friend. Very simple, just a 4-step process. Just a quick recap. We started by converting the subnet mask into binary format, and then we decided to borrow some bits from the host portion so that we get some additional networks. To find out how many bits to borrow, we use the formula 2 power x is greater than or equal to required number of subnets. Here the required number of subnets is 5. The value of x gives us 2 power 3 is equal to 8, which is definitely greater than or equal to 5. So we fixed 3 as the number of bits to be borrowed. We then found out the increment. The increment is the power of 2 corresponding to the least significant bit. The least significant bit is the rightmost bit. So we aligned the last octet against the powers of 2 and we got the value 32 as the increment. To get the new subnets in the last step, we added the increment to the original network address 192.168.1.0 and we got 8 new subnets. That's all about subnetting, my friend. Isn't that fantastic? We just took one network address and we converted them into 5 network addresses. That's efficient utilization of IP addresses. And that makes the network so much more manageable. This is just one example of subnetting. We are going to look at more examples of subnetting and some of the types of subnetting as well in the next video. So just to do a quick recap, in this video we looked at IPv4, we looked at IP addresses, we looked at classes of IP addresses, we also talked about RFC 1918 addresses, and then we talked about the loopback address. We talked about Subnet Mask, and finally we also touched upon subnetting. In the next video, we are going to continue to focus on subnetting. I hope this video was very useful to you. I'm really excited to see you in the next video, and I'd like to thank you for watching.